like to introduce Chad Lamb, who will be presenting To ROADM or Not to ROADM, When Does a FOADM Make Sense in Your Optical Network? Chad is a Chief Systems Architect at XKL and has traveled from the Seattle area to join us today. It's his first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Chad.
Thank you, and thanks to the program committee for letting me present this to you today. And congratulations, you've made it to the last talk of NANOG 92. Good job. I don't know about most of you, but I know several have traveled long and far to get here, and your bodies are just getting used to this time zone, and now you got to go right back. Sorry about that. Today, we're going to talk about ROADMs and FOADMs. And for those of you that aren't familiar with that, we're going to give you a little primer on it. We'll get some acronym soup going. I'm going to skip through that kind of quickly because I've only got 30 minutes to talk to you today, and that's going to run pretty quickly because I get a little wordy sometimes on this stuff. But then we're going to talk about what we hear from customers. I mean, after all, it's about the customer. So we want to know what are their problems, how are they dealing with them, and how can we help solve them? After that, I'm going to get into some of the topologies that are appropriate for using a ROADM or FOADM in your network, or an OADM in general. And then a little background on the architecture and comparing these two technologies. And then lastly, we'll go over a summary of just when does it make sense for you to use a ROADM, when does it make sense for you to use a FOADM. ROADM's reconfigurable OADM. A FOADM is fixed. That's the big takeaway on this slide. The rest of it you can take a look at your leisure. I really want to get to the meat and potatoes, but these are the acronyms that you'll see when you're looking at these components in your systems and from your vendors, and what does it all mean? What's a WSS? That's a big one. Wavelength select switch, and CDCF, contentionless, directionless, colorless, flex grid. That's a mouthful, right? But we're going to have some of these things looked at here in the next slides. So what do we hear from customers? I think it's really important that that we hear what you're saying and we address those concerns and those problems, right? I mean, that's why we're here. So for a little snapshot here of what we've heard customers talk about in terms of their ROADM deployments and some of their pain points, some of the software updates and fixes. They're problematic. It's a big lift, especially at layer 1 when you're trying to keep your network up. You don't want to do any software updates. If it's not broken, don't fix it. Well, some of these things are broken, so they've had some real struggles with that. Hardware failures. Sorry to say that the technology has come a long way in the last 10 or 15 years, but there's still some product out there that's a little bit suspect, and they've run into this. A WSS, the main component in a ROADM, is very custom from one vendor to another, and so once that's been integrated into a product, it's a heavy lift to go to the next generation or to make improvements or go to another vendor. So you find that ROADMs hang around for a little longer than their lifetime should be. And the software learning curve is, it can be pretty steep, especially if you're not used to dealing with any kind of a GUI or management interface that is unfamiliar to you, and the technologies and the pull-down menus and everything else. So we hear a lot of complaints about the software. The cost and complexity trade-off, that's a big deal. You've got to contemplate all of these factors when you're trying to deploy. And then vendor lock-in, these are custom, right? These are custom things. The WSS and the ROADM from one vendor is not going to be the same as another vendor. So you cannot mix and match these things in your network. Once you deploy this, it's in, and you're in for the long haul with that vendor. On the FOADM side, there are a couple elements that we hear people talk about in terms of pain points. Lack of channel balancing, that's the equalization or the power levels of the channels in your network, the DWDM channels. We'll talk about that in a few minutes as well. The cabling and the channel pre-planning. There's a bit of a lift there at the beginning when you're trying to design your network and you want to map things out. If you're using a FOADM, you need to understand exactly what channel's going where in your network and map that out for your techs to get out there and deploy it properly. And then, of course, site visits are required if you're going to make any kind of change. If you want to add channels, drop channels, you wanted to change the express channels at a particular site, whatever kind of changes you want to make, you have to go out in the field to do that, which is not true with the ROADM. So where do FOADMs and ROADMs fit in your network? Pretty much any network, except for simple point-to-point. So any place where you need to add drop traffic, you need some way to add and drop that traffic. And that's where an OADM comes into play. So for example here, site 1 to site 2 on the top diagram, pretty straightforward, simple point-to-point. You're connecting the exchange to your data center or your POP. There's no need for an OADM there. But as soon as you add something like site 2 in the bottom diagram, you have stuff you need to drop off at site 2. You need some kind of capability to do this at the optical layer. That's where the OADM comes into play. The ring architecture is the one we see the most. This is just showing you a four node ring. Make it any number you want. But typically any one of these sites is a good candidate for an OADM, FOADM or ROADM. Depends on how you like to build your network. If you want to go a lot of point-to-points all the way around that ring, that's one way to do it, but mostly people like to express some channels through. So if you want to go from site 1 to site 3, you don't want to put equipment at site 2 to have to deal with that, and so you want to express it through site 2. And I'll show you how that works here in just a second. And then of course a multi-ring or something more complicated. In this here example, site 3, that's your pain point. That's the place where you really need a ROADM to allow you to move data from one ring to the other and avoid single points of failure anywhere on either ring. So site 3 would be a good candidate for a ROADM. So let's talk a little bit about the architecture and what's involved in a FOADM and a ROADM. And these examples are going to be very simple. These are 2-degree devices. So nothing as complex as 3, 4, 9, 12 degrees. Things can get really messy. So these are the fundamental components, though, in the FOADM and the ROADM, and it applies as it scales with more degrees. In this example here, the FOADM has a handful of EDFAs to handle the egress and ingress. That's to overcome the equipment losses and the fiber losses. And then inside of that, you have your fixed filters, your channel filters, your mux-demuxes. And they come in a variety of technologies, free space filters, thin film, AWG filters, and they all have different characteristics, but they're all fixed. So the light that comes through there and what gets dropped at the channels that are shown in the black, those are the add drop channels. Those are physical cables, and they're connected to the channel ports in the FOADM. And once they're connected, they're fixed. You can't change the frequency of the light. And the red channels here, those are also cables. Those are for expressing your channels through the FOADM. And so somebody has to go out there and do the Ma Bell switch panel thing and make everything connected up the way you want it. And once it's done, it's done. In a similar architecture, now this is an example of a 2-degree ROADM. There are many different ways to build a ROADM, but this is good for comparison purposes with the FOADM. You have, instead of the, you still have the EDFAs, you still have the egress-ingress EDFAs. You have a few more EDFAs to handle the add drop, and I'll talk about that in a minute. But to replace the fixed channel mux-demux filters, you replace them with wavelength select switches, WSSs. These are the devices that allow you to change how the light passes through the device. Do you want the light to drop off at the add drop, or do you want it to express through? So you notice the red lines now just go right through inside the device. You program the WSSs to choreograph this behavior. Also notice on the add drop sites, there are more WSSs. So that's so you can have what's called a colorless ROADM. So in this example here, the reason why it's colorless is that the add drop WSSs allow you to select what wavelength you want to add and drop, and you can change it at any time. And similarly, the egress ingress WSSs this all has to be choreographed. All these WSSs have to be programmed together. But this is how you get a colorless degree 2 ROADM. Let's add some directionless to this. So in a directionless ROADM, what that means is I can send this color east or west, and I can change it later. And that's also how you handle path protection, for example. So in this case here, we've added a splitter to the architecture, and you can take that light that's coming from the add channels and send it east and west. That's all the splitter is doing. And then in the WSS itself, you would allow it to pass through or block that color. So that's how you can handle sending your traffic in any direction, and thus the term directionless. Also notice here we have something called the optical channel monitor, the OCM. That's so that you can see the different channels in the coming out of the WSSs, so you're sure you're passing what you want to pass through. There's also an equalization function, which I'll talk about in a minute. But you want to be able to monitor all the channels in the DWDM network, and that's what the OCM is doing. So keep in mind, again, this is one example of how you can build a 2-degree colorless directionless ROADM. Now also notice on the ingress of each side, it says WSS or it says an optical splitter. So you could build this with fewer WSSs, save a little bit of money, and still get the functionality that you're looking to obtain from this. So we've talked a little bit about the key elements here in a FOADM and a ROADM. It consists of the MUX demux itself, and in a ROADM that would be the WSS, the programmable component, allowing you to add, drop, or express any channels you want. In the FOADM, those are fixed. And as I said, the technology can be any type of filter technology. EDFAs are a critical part here. The equipment losses are a heavy component of all of these devices. In particular, the WSSs can be very lossy, attenuating the light significantly. But you also have the other components, the splitters, the couplers. Everything has loss, and so we have to amplify that. And then channel equalization, I'll talk about that in just a minute and what that means. But when you start adding and dropping channels, when you start expressing channels, and as you cascade that around your network, things start getting out of balance. Some channels are higher power, some channels are lower power, and that's a problem. So channel equalization is an integral part of a WSS. It will allow you to balance that power. Whereas with a FOADM, you'll need a separate equalizer in order to do that. Or some people just use attenuators and attenuate individual channels. And it really all depends on how big your network is, how many channels we're talking about, and what kind of complexity you have. So let's talk about some of the key characteristics here between in both FOADMs and ROADMs. As I said, channel equalization. Optical transceivers have a maximum and a minimum power spec at their receiver. So you can't exceed the maximum and it'll damage the device, and you can't exceed the minimum or you won't be able to recover the signal. And so all of the channels need to be within this min-max range. So that's why you have to equalize or balance the channels. At some point in time, depending on your network, how big it is, how complex it is, how many add drops you have, channel equalization is going to be a requirement if you have a lot of add drop sites. And what does that mean? You're going to attenuate the high power channels. The lower power channels are you don't need to attenuate them more. They're going to stay at that low level, and then you attenuate the high guys, so they're all the same. The WSSs have this inherently in the design of that component, so you can equalize and block channels as you want to. The other key characteristic of FOADMs and ROADMs is the optical noise and the noise sources. Noise is your killer in your network. Once it's in, you can't get it out. And so you need to be careful about the design and make sure you understand what these noise components are. Amplifiers are the major contributor, EDFAs being the biggest source of noise, but there are other things like adjacent channel interference. Adjacent channel interference is a component of your filters, whether they're fixed filters in a FOADM or they are the WSSs in a ROADM. They both have adjacent channel interference that you have to be aware of, and it's basically modeled as noise in your network. So these are some of the main contributors to noise. Okay, let's just talk a little bit in depth about some of these characteristics so that we can really assess what they mean in your network. So for channel balancing and equalization, this is showing you a simple example of a WSS that's a 1x3 WSS, so it has one common port and 3 DMUX or MUX ports. It's bidirectional. And so the WSS has the ability with you and the optical channel monitor to identify the high power channels and attenuate them so that they match the lower power channels, so everything come out at the same level. Similarly, in the other direction, when you're multiplexing together a variety of channels and you want to send them out onto your network as equals, so that when it gets to the next stage or the next location, they are reasonably within range of the min and max receive power of your transceivers. So that's what channel equalization or channel balancing, that's what its role is. And then there's channel blocking. That's also another feature of a WSS. Since you can attenuate a channel, you can also block a channel by just having the attenuation be set to its max. And so in this example, you can see you can just block any channels you want. This is where the directionless feature can come into play, or contentionless. You can make sure that the same color is not getting put onto the same fiber from two different sources. Another characteristic to be aware of, and that is true for, again, for any type of filter, just shown here as an OADM, but this is a FOADM or a ROADM, is channel narrowing. So these filters are not perfect. I think everybody realizes that there are going to be variations in manufacturability. The center frequencies are not the same for every device. So as you pass through cascaded situation in your network where you have multiple FOADMs or ROADMs, you're going to get a channel narrowing, and that is inherent with any network. And so how much that narrowing happens depends on the technology you're using, what kind of filters you're using, whether they're WSSs or FOADMs. Okay, OSNR. This is the big deal in your network. Once you get too much noise in your network, if you don't convert that optical signal to electrical signal, you're never going to convert it. It's done. If you exceed the OSNR spec of these transceivers, they die pretty quickly. Everything's running wonderfully, and then all of a sudden it's not. It really drops off like that. The new coherent transceivers that are out there today, that's how they function. In the old days with the direct detect 10 gig and lower data rate stuff, you had a little gradual decline in the performance of your link, and that's not true with these new devices. So paying attention to the noise and making sure you understand its sources is really important. So what is noise? It's basically anything that you don't want. You're looking at a signal in a channel, any other optical power that's in that channel is noise. And that can come from the amplifiers, that's the main source, nonlinear effects in the fiber. As the different channels are propagating down the fiber, like 4-wave mixing, they can negatively impact your data. And then adjacent channel power in the filters that I talked about just a minute ago. So these are all the main sources. There are others, but these are the main sources for noise in your network. And so what can you do to take care of them? Well, one of the things you can do here, and I know it's a heavy lift, it's just an equation. I'm not going to get into the details here, but the noise factor and the input power, These are the two key parameters for the noise that comes from an EDFA or a Raman amplifier for that matter. The noise factor, that's an inherent characteristic of the device you have. So go to a vendor with good quality EDFAs and you'll have a nice low noise factor. That'll contribute directly to the OSNR of that amplifier. And the other key factor here is the input power. The input power to that EDFA, if it's low, you're going to end up with a lot of noise coming from that stage. And sometimes you can't do anything about that. But we hear a lot of customers that they're trying to minimize the costs of their network, and they want to skip a site, or they want to go a little further. They want to minimize the number of locations and amplifiers. The drawback of that is right here. The input power to that next stage gets too low, and they inject too much noise, and now you got other problems. And then adjacent channel interference or suppression, depending on the technology, this is very different. I'll show that in a minute on a slide from one filter type to another. But basically, it's the light power from the adjacent channels in the filter. So whether it's the manufacturing technique used, like an AWG filter, the bonding of the fibers to the chip causes those fibers to be very close to each other, and you have light spillover from one channel to the other. And that's a that's a manufacturing flaw, not necessarily a problem with the chip itself. But that's a good example of technology that is going to cause you a lot of grief in your network with added noise. So let's just do a quick technical comparison here and show you some of the key things that we just looked at. Insertion loss. For a FOADM with a fixed filter, whether it's a free space, smaller channel count, higher channel count, AWG, whatever the technology is, you're going to get an insertion loss of somewhere between 0.8 and 6.5 dB. And what do you get for a ROADM and a WSS? It's about 7 to 11 dB. So these are just typical numbers, and it really depends on how big the device is, how many channels and ports there are on the filter. So more insertion loss means more amplifiers. Pretty straightforward. PDL, polarization dependent loss. This item here is particularly important for the higher data rate channels in your network, which I think everybody's probably looking at 100 gig coherent as a minimum, 400 gig coherent, 800 gig. These schemes, these modulation schemes, are using both polarizations in the light, in the fiber. So they're most affected by PDL, not your direct detect, the 10 gig stuff from the past. And so you have to pay attention to PDL. PDL in a FOADM for fixed channel filters, 0.3 to 0.7, and it's 1 to 1.5 for a ROADM. Doesn't sound like a lot, but it all adds up. And the other problem with the WSSs in a ROADM is that 1 to 1.5 is very much dependent on how much you're using the attenuation or the equalization function. So from ROADM to ROADM to ROADM in your network, the PDL is going to be a little bit different. And so what does this result in? Poorer performance in your transceivers. At adjacent channel isolation, we talked about that, 28 to 40 dB is the isolation number in a fixed frequency filter. That means that the channel that you're trying to pass is about at least 28 dB higher than the adjacent channel. So it's suppressing that much of the adjacent channel. In a WSS, it's a little bit worse. It's about 25. If you look at the current 400 gig ZR optics that are out there, that's the common devices that are interoperable between vendors, you need a 26 dB OSNR for that to function. So you can see how adjacent channel interference can play a factor in the ability for you to transmit and receive these higher data rate signals. And then lastly, power consumption. The FOADMs and the ROADMs both have EDFAs and amplifiers. The ROADMs will have a few more amplifiers depending on how many degrees. You basically need a pair of EDFAs for each degree, plus the add drop. And then the WSSs themselves are pretty power hungry. So it's another factor when you're considering to go with a FOADM versus a ROADM. And then lastly, a comparison here. The channel routing is done manually, Ma Bell and patch panels for the FOADM, and it's soft configurable, remotely done in a ROADM. You're cascading these devices, which you're probably going to do if you've got a network. You've got at least a couple locations where you're doing add drop. So what does that mean? You get channel narrowing with both technologies, and then you have the PDL unpredictability in a ROADM. Path protection is done easily in a ROADM at layer 1 with the blocking and the ability to attenuate the light with the WSS. In a FOADM, optical protection switching device is needed if you want to do that at layer 1. There's no inherent switching capability. Management-wise, the software is fairly trivial for a FOADM. You just have to be able to manage the amplifiers, basically. And so that can be done with whatever your existing management tools are. But with a ROADM, it's going to be using the proprietary software. Component failure in time, the fit number, obviously a device that's got power is going to fail. It's going to have a number. A device that doesn't consume power does not fail. That's why it's a fit of 1. Power consumption, we talked about that. OpEx and CapEx, so operationally speaking, for a FOADM, you have to send somebody out to make adjustments in the field, technician to make those patch panel changes. Whereas on a ROADM, you have the software component is the big lift on that. So the training and the keeping up to spec on that vendor software. CapEx, it's pretty significant. The WSSs are more than an order of magnitude more expensive, closer to 2 orders of magnitude. Depends on the size of the WSS and the size of the filters. Okay, so in summary, when do you need a ROADM? When do you need a FOADM? So do you need to make remote adjustments? Some customers have equipment in a remote location from their offices, and they have remote hands or contractors to help them make adjustments and do deployments. But if they want to try to do these kind of things remotely, then you need the remote capability of a ROADM. Do you need to do frequent add drop express changes? So that's not something that's done by tier 2s and tier 3s particularly, but they like to have that ability. So, how frequent are those changes needed? Channel balancing, we understand that's important, right? So depending on how complex your network is, long-haul networks need channel balancing. You don't necessarily need a ROADM for that, but that's a component that can be made other ways. So you can use a one-channel WSS, for example, to do channel balancing. And if you have a lot of add drop sites, then you can have a lot of unbalanced power levels. And then, so the active equalizer can be built without the ROADM. So the cost, OpEx, CapEx, we talked about that. It can be analyzed and you can figure out what makes sense for you. Failure scenarios, if that's a real pain point for you, the ROADM WSSs, they're going to fail. It's just a matter of when. And for path protection, that can be important for you if you want to do a layer 1 path protection. That's an inherent part of a WSS, very straightforward to do that. If you have a FOADM, then you need to use an optical protection switch or do your protection at layer 3. So in summary, FOADM is simple and low maintenance, low cost. It's ideal for networks that have occasional moves, adds, drops, changes, and it's a set and forget type of device. A ROADM is complex and dynamic. For larger networks, you got a lot of frequent changes, and set and don't forget. And so basically put all this together and figure out what you need. Talk to your vendors, talk to the experts, and get some advice on what makes sense for your network. That's it.
All right, thank you, Chad. I know we have one online question. You're free to queue up at the microphones if you have any questions for Chad yourselves. John Carson, unaffiliated. Are there any manufacturers who are using hollow core fiber equipment?
I wouldn't say that's terribly close to being mainstream. That's just a little off subject here, but hollow core has some complications in trying to connect that to transceivers and other components that are commonly used, and so it's not very cost effective right now, but we'll see where that technology goes.
All right, it doesn't look like we have any other questions, so thanks, Chad.
Okay, thank you.
Round of applause.